Hello and welcome. For more than 50 years, the moon has hovered above us in the night sky, serving both as a distant memory and a tantalizing promise. It was a beacon of human ambition and exploration in the late 1960s and early 1970s, when human footprints first marked its surface. This era of lunar exploration represented a dramatic burst of ambition that seemed to compress centuries of technological and scientific progress into a single decade. Yet, almost as suddenly as it began, this monumental journey halted. The rockets that once propelled humanity to the moon were retired, their launch pads falling silent. In the wake of this cessation, humanity found itself remaining in low Earth orbit, content to circle its home planet instead of venturing outward into the vastness of space. Now, that long pause is finally coming to an end. The mission that heralds this new chapter in space exploration is known as Artemis II, the first crewed flight of NASA's Artemis program. This mission is not merely a symbolic return to the moon. It is a deliberate, meticulously engineered step forward toward building a permanent human presence beyond the confines of Earth. Artemis II carries with it the latest technology, new political realities, innovative commercial partnerships, and a fresh generation of astronauts. These astronauts grew up not on Apollo landings, but watching space shuttle launches and broadcasts from the International Space Station, shaping their dreams and aspirations. This time, the moon is not envisioned as the finish line, but rather as the beginning of a new era of exploration. The reasons for returning to the moon in the 21st century are intricate and multifaceted, far more complex than the motivations that drove the Apollo era. During the Cold War, lunar exploration was fueled by intense geopolitical rivalry. Planting a flag on the moon became an unmistakable demonstration of technological superiority, a symbolic victory in the space race. Once that formidable goal was achieved, the urgency quickly faded. In contrast, today's return to the moon is driven by a different logic. The moon is no longer viewed as a distant trophy to be claimed, but as a strategic platform. It is close enough to Earth to allow for a relatively rapid return in case of emergency, yet far enough away to expose astronauts to the true conditions of deep space. In this environment, radiation levels are higher, communication delays become measurable, and systems must function autonomously without immediate ground intervention. Every challenge that future Mars explorers will face begins to emerge once Earth shrinks to a small marble in the window of their spacecraft. There is also a profound scientific awakening tied to the exploration of the lunar poles. Instruments aboard orbiters have detected evidence of water ice within permanently shadowed craters. These regions, shielded from the sun's warmth, preserve frozen deposits that may have existed for billions of years. Water in this context is more than just a resource for survival. It is a gateway to propulsion. When split into hydrogen and oxygen, water becomes rocket fuel, which could lead to the establishment of a refueling infrastructure on the moon. Such infrastructure could transform the economics of deep space exploration. Beyond engineering and resources, the moon offers something unique in the field of science: silence. The far side of the moon is shielded from Earth's radio noise, making it one of the quietest places in the inner solar system for radio astronomy. From this vantage point, scientists could observe the early universe with unprecedented clarity. The motivations are practical, scientific, and philosophical all at once. The moon is envisioned as a laboratory, a fuel depot, a stepping stone to worlds beyond, and perhaps eventually a home for humanity. When Apollo 17 departed the moon in 1972, few could have imagined that it would be the last human visit for more than 5 decades. Yet, the pause that followed was shaped by economic realities and political recalibration. The Apollo program was expensive on a historic scale, and once its primary objective was fulfilled, maintaining that level of funding became increasingly difficult to justify. Attention shifted toward building reusable spacecraft capable of routine access to low Earth orbit. The space shuttle promised frequent missions and broader participation in space science. Later, the International Space Station emerged as the centerpiece of human spaceflight, focusing on microgravity research and fostering international cooperation. Technologically, the ambition of sustaining a lunar presence exceeded what was feasible at the time. The Apollo missions demonstrated that humans could reach the moon, land briefly, and return safely to Earth. However, they did not establish the infrastructure necessary for permanence. The materials science, computing power, autonomous systems, and commercial ecosystem required for sustained operations simply did not exist at that time. In the decades since, those capabilities have matured significantly. Modern spacecraft now benefit from digital navigation, advanced composite materials, and lessons learned from thousands of hours spent in orbit. The private sector has become an active partner in space development, with reusable rockets altering the economics of launching into space. A return to the moon now fits within a broader strategy rather than standing alone as a singular, isolated achievement. At the heart of this new era stands Artemis II. Unlike its predecessor, Artemis I, which flew without a crew to test systems in 2022, Artemis II will carry 4 astronauts on a journey around the moon. The mission will launch aboard the Space Launch System, or SLS, a towering heavy-lift vehicle specifically designed to send substantial payloads beyond Earth's orbit. The SLS produces more thrust at liftoff than any operational rocket today, propelling the Orion spacecraft out of Earth's gravitational embrace. Inside the fairing sits the Orion capsule, a spacecraft built specifically for deep space missions. Orion's design reflects the lessons learned from Apollo, while incorporating the best of modern engineering. Its life support systems are designed to regulate atmosphere and temperature for longer durations. Its avionics manage navigation with a level of digital precision that was unimaginable in the 1960s. Its heat shield must endure re-entry speeds exceeding those of spacecraft returning from low Earth orbit. Artemis II will not land on the moon. Instead, it will follow a free return trajectory, looping around the lunar far side before naturally curving back toward Earth. This path is both elegant and cautious. If propulsion systems fail at a critical moment, gravity itself will guide the spacecraft home. During the mission, the crew will travel thousands of kilometers beyond the moon, venturing farther from Earth than any human has before. For several days, Earth will appear as a distant sphere set against the blackness of space, a poignant reminder of both human fragility and ingenuity. The crew of Artemis II represents the evolution of space exploration into a more inclusive and international endeavor. Reed Wiseman, the mission commander, brings with him a wealth of experience as a naval aviator and former chief of NASA's astronaut office. Before his selection for Artemis II, Wiseman spent months aboard the International Space Station, conducting scientific experiments and performing spacewalks. His leadership style is described as calm and methodical, qualities that are essential when operating far from immediate ground support. Serving as pilot is Victor Glover, a naval aviator and test pilot who previously flew on SpaceX's Crew 1 mission. Glover's career blends operational precision with engineering insight. As the first Black astronaut assigned to a lunar mission, his role carries historical significance alongside technical responsibility. He has spoken often about inspiring younger generations to see themselves in the exploration narrative, encouraging them to dream big and pursue careers in science and technology. Mission specialist Christina Koch holds the record for the longest single spaceflight by a woman. During her nearly year-long mission aboard the International Space Station, she conducted research spanning biology, physics, and Earth observation. Her endurance and scientific focus make her uniquely suited for deep space travel. She will become the first woman to travel beyond low Earth orbit, marking yet another significant milestone in human space exploration. Completing the crew is Jeremy Hansen, representing the Canadian Space Agency. Hansen is a former fighter pilot and engineer, and his selection marks the first time a Canadian astronaut will journey to the moon. His presence reflects the international partnerships that underpin the Artemis program. Canada's contributions to lunar exploration include advanced robotics and participation in future lunar infrastructure projects. Together, these 4 astronauts embody experience, diversity, and global cooperation. Each member of the crew has trained extensively in simulations, replicating launch vibrations, deep space isolation, emergency scenarios, and high-speed re-entry. Their journey is not a solo triumph, but the culmination of the efforts of thousands of engineers, scientists, and technicians, working in concert across the globe. Artemis II is currently targeted for launch in 2026. Deep space missions operate on a cadence defined not only by engineering readiness, but also by the celestial mechanics of space travel. Launch windows must align with lunar positions to ensure safe trajectories. Once launched, the mission is expected to last roughly 10 days. The timeline unfolds like a carefully choreographed sequence. After liftoff, the spacecraft will enter temporary Earth orbit for systems checks. Then comes translunar injection, a powerful burn that sends Orion hurtling toward the Moon. Several days later, the spacecraft will approach the lunar far side, disappearing briefly from direct communication with Earth. As it arcs around the Moon, gravity will bend its path back homeward. The return journey culminates in atmospheric re-entry at velocities exceeding 39,000 kilometers per hour. Plasma will envelop the capsule, temperatures rising dramatically before parachutes deploy and Orion splashes down in the ocean for recovery. Those 10 days compress decades of preparation into a brief, yet intense experience. Although Artemis II is primarily an engineering validation mission, its scientific implications are profound. Human bodies respond differently to the deep space radiation compared to the relatively sheltered conditions of low Earth orbit. Sensors and biomedical monitoring will collect valuable data essential for planning future long-duration missions. Navigation and communication systems will be stress-tested under real deep space conditions. Delays, autonomy, and onboard decision-making will all be evaluated. Engineers will analyze how spacecraft systems perform under prolonged exposure to radiation and thermal extremes. Perhaps most importantly, Artemis II restores a capability that has lain dormant for half a century, the ability to send humans beyond Earth orbit. That capability itself becomes a scientific instrument, enabling future missions that robotic probes alone cannot accomplish. Artemis II is not an endpoint. It is, in fact, a rehearsal, a dress rehearsal for what is to come. The next major milestone will be Artemis III, which is intended to land astronauts near the lunar South Pole. That mission will rely on partnerships with commercial industry for its human landing system. Orbiting above the Moon, the planned Lunar Gateway will serve as a staging hub for surface expeditions. It will function as both a research platform and a communication relay, as well as a docking node. Over time, the architecture of this system could expand to support sustained operations on the lunar surface. Future missions may involve habitat construction, resource extraction experiments, and preparation for voyages to Mars. Each step builds upon the previous one, turning short visits into enduring presence. The return to the Moon is not a mere repetition of history. It is a reinvention of purpose. Artemis II carries with it the weight of expectation and the optimism of possibility. It connects generations who watched the grainy broadcasts of Apollo with those who grew up streaming high-definition launches on their mobile devices. It represents a shift from competition to collaboration, from singular achievements to a sustained strategy for exploration. When Orion's engines ignite and the Space Launch System rises majestically from the launch pad, it will signal more than just the start of a mission. It will mark the reopening of a frontier that has waited patiently in the night sky for humanity to return. This time, humanity is not going back simply to touch the surface and then leave. This time, we are going to learn how to stay.